Welcome to this application presentation of digital image correlation, or DIC, being used for compression, bending, shearing, and forming limit curve, or FLC, testing. Here is an overview of applications that will be presented in the compression, bending, shearing, and forming limit curve, or FLC, testing presentation. Application 1 was a gripping test performed on a chromolybdom steel water pipe wrench measured using the FlexDIC system. The measurement objective was to measure the principal strain 1, or the major strain, on the wrench to determine the strain localization to the gripping of a screw head. In figure 1 to the top, a ISTRA 4D 2D overlay visualization of the Lagrangian principal strain 1, or major strain, in microstrain can be seen. The red areas are subjected to tensile loads, areas of high strain localization, and the blue areas to compressive loads due to the stress of compression. This measurement application is courtesy of Lima's Messtechnik and Software GmbH. Application 2 is a pressure vessel test application, specifically being a compression test of a carbon fiber reinforced plastic overwrap cylinder. This measurement application was performed using the FlexDIC system, whereby the objective was to determine the strain distribution and localization during the test and to measure the principal strain 1 before fracture. In figures 1 and 2, the camera run field of view can be seen before the test and after the test. Notice in the fracture after test, the individual CFRP overwrap bands can be seen. In video 1 to the left, we see the ISTRA 4D 3D model visualization of the displacement grid with rigid body motion removed. The green grid is the reference and the red grip is a step measurement. As can be seen, the compression test shows that the CFRP overwrap did not displace uniformly, indicating local buckling. In video 1 shown to the right, the 2D overlay visualization of the Lagrangian principal strain 1 in millistrain can be seen. It is clear during the test that the localization of strain occurred in the direction of load application, not along the hoop overwrap. The advantage of DIC is that strain localization, aka the identification of weak spots, can easily be identified using the technique. The strain value and position of strain localization can be detected based on a full field deformation and strain map. Application 3 is a compression test with a load offset from the center axis. The 3D printed ceramic material was measured using the FlexDIC system. The measurement objective was to determine the strain distribution and localization during the test and measure the principal strain 1 before fracture. In video 1 shown to the top, the ISTRA 4D 2D overlay visualization of the Lagrangian principal strain can be seen. It is clear that during the test that the localization of strain occurred in the bottom right-hand corner, exactly along the direction and axis of loading. The fracture is also quite rapid, indicating the brittleness of the material. Only 30 millistrain was required to fracture the specimen in compression. Figures 1, 2, 3 to the right are ISTRA 4D 2D overlay visualizations of the displacement in X, Y, and Z respectively, with the rigid body motion removed up to point of failure. It is clear to see the effect of the offset compressive load on the material and where the material deformed most during the test, specifically in the bottom right-hand corner. Application 4 is a compression test with a load applied in the vertical direction marked as a pink arrow on the connection point to the saddle. The CFRP bicycle frame was measured using the FlexDIC system. The measurement objective was to determine the maximum point and amount of deformation from the applied load. In figure 1 to the top, the ISTRA 4D 2D overlay visualization of the displacement green with a 20 multiplication extension factor can be seen. The green grid is the reference and the red grid is the step measurement. As can be seen, the compression test shows that the CFRP bicycle frame deforms considerably under the applied load. In figure 2 shown below, the ISTRA 4D 2D overlay visualization of the displacement total in millimeters can be seen. The point with the highest displacement is marked within the pink circle and is approximately 11 millimeters. This measurement application is courtesy of Limas Messtechnik. Application 5 is a 3D printed rubber test, performed and measured using the FlexDIC system. A compression test was performed of the 3D printed rubber specimen. The measurement objective was to determine the maximum point and amount of strain from the applied load. In figure 1 to the right, we can see the ISTRA 4D 2D overlay visualization of the total displacement in X and Y respectively, and the major, minor and shear strain respectively at maximum load. In video 1 shown at the top, we see the ISTRA 4D measurement acquisition steps of the compression test, courtesy of Limas Messtechnik. In figure 2 to the top, the ISTRA 4D 2D overlay visualization of the Lagrangian principal strain can be seen in percent at a maximum compressive load. The max strain is 24% at the upper left-right flanks of the rubber specimen marked within the pink circle. Application 6 is measured using the MulticamDIC system. A cylindrical foam sample was loaded under compression. The measurement objective was to perform a 360-degree coverage inspection of the cylinder sample to identify points of buckling due to the compressive load. In figure 1 to the right shows the reference measurement acquisition for each of the 8 cameras used in the MulticamDIC setup. An ISTRA 4D 2D overlay visualization of the contour with respect to the distance to a best fit sphere in millimeters for each of the 8 cameras can be seen. Multi-camera DIC systems enable increased field of view and is perfect for the measurement of curved objects. Every 2 cameras observe the same field of view. An overlapping area is required between the 2 fields of view for multi-camera DIC measurements. In figure 2 to the left shows the image of the multi-camera DIC test setup used with 8 cameras orientated around the cylinder in a 360-degree formation. Each camera observes a 45-degree segment of the cylinder at the same standoff distance. This measurement is performed using one setup using one global coordinate system. As such, no measurements are stitched or transformed in post-processing. Figure 1 to the right shows the ISTRA 4D 3D model visualization of the contour using a cylindrical coordinate system. As can be seen, the complete 360-degree surface structure contour is measured. In figure 2 to the top, there is an ISTRA 4D 3D model visualization of the Z displacement, being the outer plane displacement, with rigid body motion removed in micrometers. It is clear from this image that approximately the same amount of buckling occurred at 2 positions on the foam cylinder and deformed at 2.3 millimeters. In figure 3 to the top showed an ISTRA 4D 3D model visualization of the Y displacement in outer plane with rigid body motion removed in micrometers. Figure 4 shows an ISTRA 4D 3D model visualization of the engineering principal strain 2, or the minor strain in percent, with a spatial plot of the marked pink line, with the Lagrangian principal strain shown in percentage. Video 1 to the right shows an ISTRA 4D 3D model visualization of the engineering principal strain 2 during loading. Application 7 is a compression test applied through a hydraulic cylinder of a cylindrical composite pipe with 2 meters in diameter. The measurement system used for this application was a MulticamDIC. The measurement objective was to perform a 180-degree coverage inspection of the inner wall section of the cylinder sample to identify point and amount of buckling due to the compressive load. In Figure 1, the schematic diagram shows the test setup with the marked field of view sections for cameras 1 and 2 in dark green and cameras 3 and 4 in light blue. In Figure 2 to the left shows the image of the MulticamDIC test setup used with 4 cameras orientated within the pipe and inspecting the inner 180-degree wall section. The load direction is marked F in pink. The multi-camera system enables increased field of view and is perfect for the measurement of curved objects. Every 2 cameras observe the same field of view. An overlapping area is required between the 2 fields of view for multi-camera DIC measurement. This measurement is performed by using one global coordinate system, and as such, no measurements are stitched or transformed in post-processing. In Figure 3 shown to the left is the applied speckle pattern of the inner wall of the composite pipe, which is prepared with the DSM 50650 speckle pattern kit stamp rollers. The pipe was rotated 180 degrees for measurement. Using the stamp roller, the optimal speckle pattern size could be applied for the given field of view, camera resolution, and required accuracy. In Figure 4 shown to the top shows the reference measurement acquisition for each of the 4 cameras. Video 1 to the right shows a 3D model visualization of the displacement grid with rigid body motion removed. The green grid is the reference and the red grid is the step measurement. The pipe deformation caused by the hydraulic cylinder can be observed. Video 2 to the right shows a 3D model visualization of the engineering tangential strain X in millistrain. The X direction was defined along the curvature axis. Below is a temple plot of the analog load in kilonewtons and the engineering tangential strain X of the virtual point gauge 0.1. One can see that at maximum load there is also maximum strain at the point gauge indicated in pink. Video 3 below shows a 3D model visualization of the engineering tangential strain Y in millistrain. The Y direction was defined as being perpendicular to the curvature axis. Figures 1, 2 and 3, shown at the top, show the ISTRA 4D 3D model visualization of the engineering tangential strain in X, Y and shear strain XY in millistrain respectively. The X direction was defined along the curvature axis. The strain presented is acquired at the measurement step with the peak load. A line gauge is applied along the y-axis, which is perpendicular to the curvature axis marked in pink. In Figure 4 showed to the right a spatial plot of the line gauge with X strain, Y strain and XY strain at the measurement step can be seen. The X strain is marked and shown as black, the Y strain in red and the XY shear strain in blue. Application aid is a compression test using an aluminium wedge on a silicon cube measured using the FlexDIC system. The measurement objective was to measure and validate the DIC measurement using the FEA approach in ANSYS. In Figure 1 to the left, we see a picture of the test setup with 1, the silicon cube and speckle pattern, and 2, the aluminium wedge. Video 1 to the top shows a 2D overlay visualization of the displacement in Y direction in millimeter. The Y direction was defined along the loading axis. The maximum Y displacement is 6.5 mm, shown in purple. Video 2 shows the ISTRA 2D overlay visualization of the displacement in Z direction in millimeters. The max Z displacement is 2.35 mm, shown in red, away from the camera. Figure 2 to the left shows a schematic diagram of the FEA input. 1 is the alternative silicon of unknown properties. 2 is the wedge made from structural steel. U indicates the applied displacement from load. C indicates the point of contact and friction. And A indicates the points of fixation. Figure 1 to the right shows the ISTRA 4D 2D overlay visualization of the true principal strain 2 or minor strain in percent. The measurement step is shown at peak load. The peak strain is 27%. A virtual gauge line can be seen in the visualization. Below, a spatial plot can be seen for the respective step. indicating the true principal strain 2 along the line. Underneath, a temporal plot can be seen indicating the accumulation of strain during the test. In video 1 shown to the top, an ISTRA 4D 3D model visualization of the true principal strain 2 minus strain in percent can be seen. In figure 1 to the top, we see the ISTRA 4D measurement of the principal strain 1 or major strain. In figure 2, we see the FEA simulation of the principal strain 1. In figure 3, we see the difference between the DIC measurement and the FEA simulation. Application 9 is a bending test performed on a micro specimen with length of 4 mm and width of 0.3 mm. This measurement application was performed using a FlexDIC together with a stereoscopic microscope. The measurement objective was to determine the maximum point and amount of strain from the applied load. Figure 1 to the top shows a picture of the test setup with a FlexDIC system attached to a stereoscopic microscope with a horizontal adapter. Video 1 to the left shows an ISTRA 4D 2D overlay visualization of the engineering principal strain 1 in millistrain with 1 point gauge element. A temporal plot below depicts the analog load input and the engineering principal strain 1 of 0.1. The maximum load is circa 2 newtons and the peak strain is 70 millistrain. In figure 1 to the right, we see the ISTRA 4D 2D overlay visualization of the displacement in the x direction in micrometers with rigid body motion removed. The x direction was defined to be in the horizontal direction with respect to the image. The peak displacements are minus 30 micrometers and 190 micrometers. Application 10 is a bending test of 2 glued or bonded plastic plates measured using the FlexDIC system. Figure 1 and 2 show an ISTRA 4D 2D overlay visualization of the Lagrangian tangential strain in x in percent. The x direction was defined to be in the horizontal direction with respect to the image. Figure 1 is acquired at 39, i.e. during the test, and figure 2 is acquired at step 50 at the end of the test. This shows the compressive strain blue and the tensile strain red on the bonded sample in the color bar. After the failure of the bond in step 50, the tensile compressive strain is distributed over each individual panel, indicating that the bond is no longer carrying the strain load. In figure 3 and 4, we see the spatial plots of the virtual line gauge with respect to the tangential strain x. Figure 3 is acquired at step 39, i.e. during the test, and figure 4 is acquired at step 50 at the end of the test. This application is courtesy of Limas Mesh Technique. Here is an overview of applications that will be presented in part 2 of the compression, bending, shearing and forming limit curve testing presentation. Application 11 is a shear test measured using the FlexDIC system of a V-notch sample. The measurement objective was to determine the amount of strain applied from the shear load. Video 1 to the right shows the ISTRA 4D 2D overlay visualization of the Lagrangian tangential shear strain in percent. The peak shear strain is minus 70%. Application 12 is a forming limit curve or FLC test according to ISO 12004-2 of a Nakajima test specimen. Application 12 was measured using a FlexDIC system for the determination of the FLC parameters according to the norm. Users can scan the QR code to watch the application video. Video 1 to the right shows a 4D 2D overlay visualization of the Lagrangian principal strain 1 or major strain in millistrain with 1 virtual line gauge element. A spatial plot, shown below, indicates the principal strain with respect to distance along the gauge line. The peak strain for the application is 820 millistrain before fracture. Figure 1 to the right shows the ISTRA 4D application scripting module for determination of the forming limit curve. The fitting area must be set by the user. After the calculation of the second derivation, the fitting window area can be determined based on the ISO 12004-2 norm. Click the FLC calculation button and then the FLC parameter as limit strains 1 and 2 will be calculated. The test report shows detailed information on the data evaluation. Figure 1, shown to the right, shows the ISTRA 4D application scripting module for the determination of the forming limit curve safe, shown in green, marginal, shown in yellow, and red, shown as damaged sections. The major and minor strain for each point is plotted from the last measurement step. Figure 2, shown on the far right, shows the 3D model of each coordinate point with the indicated safe, green, marginal, yellow, and red damaged sections. This concludes the material testing, compression, bending, shearing, and forming limit curve testing application presentation. If you have any questions or comments, please contact your local Dantec Dynamics sales representative or email product.support@dantecdynamics.com.